So our first speaker is Miki Tebeka. Correct me
Tebeka.
if I'm Tebek?
Tebeka.
Tebeka. Okay.
Yes.
An old-timer, teacher, mentor, book writer, conference organizer, videos author, hacker, hacking with Go, Python, and several other languages. And he will be speaking about simulations of the for the mathematically challenged. Welcome.
Thank you. So
share screen.
Here I go.
Yep.
Okay.
Perfect.
So simulations for the mathematically challenged. That includes me, of course, and I'm married to a math teacher, so I need to get by it. So my name is Miki Tebeka. I've been a professional developer for 25 years now, starting at Intel around 97-ish. Worked with Python most of the time, and then around almost when Go came out, something like 11 years ago, I started playing with Go, even before we had the Go tool, with all these funny makefiles and other things. And since then, about 50-50 of my time is Python and Go. I teach a lot in my company and consult with other companies. And because I work also a lot with Python, and I'm building infrastructure for data scientists. I'm not a data scientist. I'm not researching algorithms and training models, but I build systems for people who consume the data. And I also help models get into production and work there. And I'm doing it in both in Python and Go, and sometimes together with Python and Go in the same project. I have some interesting thoughts about this area of Go and data science and how we can do that. So the story goes that, by the way, pardon for my English, I'm not a native English speaker. I spent 8 years in the United States, which only made it worse. So if you don't understand something, please just ask questions, or in general, ask questions. Otherwise, this will be over pretty quickly. So our story goes that you have some problem at work. Let's say you have some load balancing issue, or just a general load issue problem, and you want to see if adding a database, or maybe adding a new one of the web servers, which one is going to impact the traffic best, because you have limited resources. And you know how many requests are coming per day, but this is some statistics is involved, right? If I'm going to do that, will this one work better than the other one on average, or on median, or 99th percentile, or whatever? So you head out to the internet, and the internet start giving you Bayes theorems and standard deviations and entropies and z-scores, and also throws the whole Greek alphabet at you, and you don't understand anything. And that's where most of the developers are saying, okay, I'm not going to do that. They back off. They say, I will let someone else, data scientist, someone who learn statistics, I'll give them the problem, and they solve it for me. And I want to show a way that is easier, and it's very, very effective. And Jake Vanderplas is coming from the Python side of things. He's an astrophysicist who's very highly involved in the Python data science community. And basically, he says if you can write a for loop, you can do statistics. That's it. And I'm guessing that most of us on a good day without too many beers can write a for loop. So we should be good at doing that. So the idea is to run what is known as simulation, or Monte Carlo simulation, sometimes it's known. This method is very old. It's been used in the Manhattan Project, where they developed the atomic bomb. And since then, it's used everywhere. And I want to show you several ways of using these, and hopefully convince you that even though if the problem seems like mathematically it's hard to understand, you can easily solve it with a little bit of math.rand and a for loop, and that's it. So what are we going to do? We're going to solve 5 problems. One is we're going to figure out which is the best tile in the game of Catan we want to place our houses or our tiles next to. Second, we're going to calculate pi, the ratio between the circle circumference and the radius. Then we're going to talk about the birthday problem. What are the odds that, let's say, a group in the size of what we have here, what are the odds that 2 people here have the same birthday? Then we'll look at something which is relevant about the validity of medical tests. And finally, there will be goats. So let's talk about the first one. So the first one is the game of Catan. In the game of Catan, you have these tiles, these 6-sided tiles, hexa, not hexa. I forgot the name. Tiles, and they have numbers on them. And the idea is that you put your game pieces next to them, and then you throw 2 dice. And then you get a number between 2 and 12. And whichever number you get resources from the tile that has the same number on them. So the question is, which ones have higher probability of finding of two dice roll to get the number, right? So that's what we're going to look for. So let's have a look at the code. So first we are going to simulate a dice roll. So a dice roll is really easy. We're going to use the round model. Int returns what is known as a half open range, meaning you get between 0 up to, but not including the number you give it. So if you give it 6, it's going to give us 0 to 5. We want 1 to 6, so we just add 1 to the number, so we get the numbers between 1 and 6. And then we just run a simulation. And the simulation basically starts with an empty map of counting for every number how many times we saw that number in general. And then we run the number of runs, do a 2 dice roll, and increment the counter for that number. So after this stage, we have a map with the keys are numbers between 2 and 12. You can't get 1 with the 2 dice roll. Between 2 and 12. And the values are the number of times we saw them. We want to convert it now to fractions or percentage. So we're going to create another map, which is from the number, like 2 or 4, to the fraction of how many times, what's the odds that we're going to get this number. So we're going over the counts, basically just dividing the count for the specific combination of 2 dices by the total number of runs, and update our map. And finally, we return. And we are going to run this. This is before you run, you might think about seeding the random number generator. So random numbers in computers are not really random, right? They started, if you know the seed, the initial number, you can know the whole sequence. It's deterministic. Now, there is a story about a few years back, someone found out the random seed for an online poker company. He cleaned the house. He knew exactly which cards are coming in. He made a lot of money. They tried to fight him, but the court said, your problem. So they did that. Some languages like Python, they automatically seed the random number generator when the program starts. Go does not. So if you want to seed it, usually it's custom to seed it from the current time. So every time you do a run, you'll get a different seed, and then you'll get different results. The problem is that if you're doing testing, then you get different results every time. It makes it hard to test. So when we test, we usually seed it with a known seed, so we can compare results. We're going to run 1,000,000 simulations, right? Got to love the underscores in numbers, right? make them much more readable. And then I'm going to print out for every possible number that we can get from a 2-dice roll, what are the odds. So when we run it, unsurprisingly, we see that 7 is the best number. What is the problem with this solution? Anyone plays Catan? Nobody plays? There's no 7 in Catan.
I just wanted to say you move the radar, or I don't know what's it's called in English.
Yeah, so in Catan they have numbers for the tiles, but 7 is not there. So our 2 best ones are 6 and 8. These are the ones that you have high probabilities. And if you're going to do that and check the math later on and do actually the all combinations and count them, you will get the same distribution. That's the same thing that is there. So something which is not, I don't think this code is very complicated. You don't need to do statistics and a lot of things. I usually, once I'm doing the simulation and I get some results that looks fine, I have a good friend who's actually an algorithmic, and I go say, does this make sense? And he said, yeah, you're fine. You're not doing something bad. So sometimes it's good to double check, but just to get the initial idea is easy. Now we're going to calculate pi, which is interesting. How are you going to simulate pi? So this is involve a little bit of math, but hopefully not too much. So the idea is that we are going to pick a circle with a radius of 1. Okay, so if you look at the area of the circle, this is pi times r squared. So the area of the circle is exactly pi. And what we're going to do is we're going to look at this square on the top right corner, and then we're going to count, and we're going to pick random points. And for every random point that we pick, we're going to see, did it fall inside the square by doing the calculation, the Pythagoras formula, or not. And eventually, once we finish the simulation, we'll have the ratio between the points that were inside the square and the points that outside the square. This ratio is exactly 1/4 of a pi. So we just need to multiply this ratio by 4, and we are going to get pi. So code. Pi. So we're going to calculate pi. So the radius is 1, and we are going to count how many inner points there are, and n, the parameter to the function, is the total number of simulations that we're going to do. So again, we're going to run up to n. We're going to compute 2 points, and here we're going to get round float 64. And float 64 gives me between 0 and 1 a number. Sorry. And then we're checking using Pythagoras if it's inside or outside. And finally, we calculate the ratio, which is the number of the inner points divided by the number of the total points, which is n. And then we return 4 times the ratio. And to do that, I'm going to run it, to get a good approximation, I'm going to run it a little bit more. So this time I'm going to run it 100 million times. Which gives me time to talk over it, right? But not bad, right? So it's not a lot of time. Go is pretty fast. That's why one of the reasons we like Go. And we got a good approximation of pi. Any questions?
Yes, short question. You are doing Pythagoras there. Yes. I don't think you need the square root. I think you can square the radius beforehand, and then just compare those two. that should
No,
speed
I
up
need to.
your.
Yeah, I can square the radius as well. Yeah, you're right.
Yeah, so
What
I
am I
mean,
going to square the radius? It's going to stay 1. So I
yes,
can.
so you can just lose the
Oh, now I'm
math.sqrt.
intrigued.
Maybe it gets faster.
I
I hope.
So you know what? Let's. Really unscientific. Never do benchmarks when you're running Zoom. That's not the way, but and then we don't need math. No, about the same.
Yeah. Okay.
I'm not sure. Again, running benchmarks when you're talking in Zoom, it's not indicative of anything, but it's a good point. Yeah. All right. The next one is about the birthday problem. Okay, so I've already said that in Zoom, he's always reminded of this scene from the Muppet Show. Everybody's looking like this, and the question is, say we have a group of 22 people. What are the odds that 2 of them are going to have the same birthday? And birthday, I just mean not the year, but just the date and day in the month. Any guesses? No, 6. Okay, keep it in your heart. You don't have to say. Okay, so what are we going to do is we're going to get a group and we're going to run a simulation. And the day that we're going to encode birthdays, it just as a number between 0 and 364. That's what we're going to do. So we're going to keep off the birthday we've seen. We're going to run a loop for the number of people. And then we're going to take a random day in the year. And then if we saw this day already, it means that we have at least 2 people with the same birthday, we return true. Otherwise, we return false. We finish the whole, So this is a single simulation, and we are going to run it for this number of runs. So we're going to count how many random groups had at least 2 people with the same birthday. So we're going to run the number of runs, and if we have a match, we increment the same counter, and finally we divide one by the other, and we get the results. Okay, so I took a group of 23. Sorry, if I ruined your calculation about 22 people, it's going to be 23 people. And again, I'm going to run it for a million of times. So I'm going to basically like sampling million group of 23 people and see what's going on. And this is usually a surprising result. So there's a 50% chance, and this is mathematically correct. If you're going to check the math behind it, this is mathematically sound. And this is one of the things that always shows me that, or shows people that our intuition about statistics is usually wrong. And you need to run something, you need to do numbers. Even people like Nassim Taleb, who's a genius at statistics, says that his biggest challenge is fighting his own intuition, and he runs simulations or do the math or whatever. But a lot of time the intuition, most of the people give it a way lower percentage than that. But we know that it's not always like that. Right, so the chances of a piece of bread falling on the butter side is directly proportional to the cost of the carpet. Right, there's a correlation to Mr. Murphy. It's an awesome read. There will be a link to the slide, so you can read it there. It is nice. And the thing is that we used what is known as I got a blackout on the name. It's a distribution where every value has the same probability of hitting. So we're saying that all people's January 12 or October 13 have the same, you have the same probability of being born on these days. Even distribution. Okay, I got the name. And if you look and the numbers, and these are the numbers, someone did the work going on the US Census. So in the United States, these are the chances of you being born on given dates. And you see that some dates are the higher, the deeper the color, the darker the color, there are more chances that you're going to get on this. So the distribution is not really even distribution like we did that, but it's different than what you think. And this is something when you're doing simulation, this is very important. You need to know how your data is distributed. But luckily, it's super easy to know these days because a lot of time you have the data already. So calculating what are the odds of a single day happening, it's like what we did here in the census, right? We just counted for every day of the year how many people were born on this day, and then did the math for every. And on the top there is a famous quote from George Box saying that all models are wrong. So our model is wrong, but some are useful. So every model is a simplification. You're always doing something. You can't really emulate the true world or what's happening, but you can get close enough so things will be useful. And when I changed the code of the simulation to use this, what is known as weighted probabilities, I got the same result by a fraction. So even though we assume that it's even distribution, even it's not, it was still a good result. It still gave us a good hunch of what's coming in, to know that even, so it's going to be 0.5, maybe, give or take a little bit, but we're still in the ballpark. We're still knowing what to do. So the simulation was useful, even though we made some really crude assumptions about how things are. This one comes from, there's a book called Fooled by Randomness by, again, Nassim Taleb. He also likes black swans and anti-fragile things and many other things. And he talks about this question that they ask a lot of, he presented it to several doctors to see if they get it right. So the idea is that you have some kind of a test for a disease. Let's say checking if someone has COVID or not, right? It has a 5% false positives, meaning 5% of the time it will tell you that you are sick even though you're not sick. And now we know that the disease is striking 1 every 1,000 people. And then said you pick a random person, you test it for the disease, and it comes out positive. What is the probability that they are really sick? Okay, and again, think in your mind, what do you think the odds are that, this test, someone came in, pick a random person from the street, give them a test, they came positive, and now what is the odds that this person is really sick? And this has a lot of implications, right? If you're going to send someone to do a treatment that might cost a lot of money or be very invasive or something else. So you really hope that the doctors know the statistics. Spoiler, they didn't, but we're going to talk about. So a little bit about terminology. So when we talk about what is known as a classifier, which this test is basically saying if a person is sick or not, this is known as the confusion matrix. And I like the name confusion matrix because I'm always confused by the confusion matrix. But the idea is that you want to be on the diagonal from the top left to the bottom right. So if someone is predicted sick and they are actually sick, this is true positive. And on the bottom right, if they're actually healthy and they predicted healthy, this is known as a true negative. And on the left, bottom left to top right, this is the bad stuff. This is the wrong predictions. And we talk about the false positives, which are on the lower left, meaning someone who is actually healthy, but predicted sick. And this is something we don't know. Okay. So we start with the function of saying this is a chance in something. So I want something. We said that disease is striking 1 in 1,000 people. So I want an event 1 in 1,000, and also 20% or 5% positive. It's also 1 in 20 chance. So basically what I'm saying is pick me a random integer and tell me if it's 1 or not. So let's say if n is 10, so I have possible 10 numbers, and only 1/10 of the number is going to pick 1. So this function is going to return true 1/10 of the time that you're calling. And now we can check if someone is sick. We can say this is 1 chance in 1,000. And then we'll say about diagnosed. So I'm getting a random person, and in a simulation, you know everything. So you know if you already picked a sick person or not. So I want to say when I'm picking a person, if they're sick, we assume that the test is 100 correct. This is not specified in the question, but this is the assumption we're doing. Otherwise, we're saying that if they are healthy, there's 1 in 20, 5% chance that the test is going to say that they are truly sick. And now we're going to run the simulation, basically pick a random person, and then we know if they're sick or not. We just give the odds. And then if they're sick, we're going to increment the number of sick people. Then we're going to run the test on the same person. And if they were diagnosed as sick, we're going to increment the number of diagnosed. And finally, we're going to return the number of sick people divided by the number of diagnosed, saying what is the chance that if you are diagnosed, you are actually sick. And we're going to run it for 1,000,000 times. Again, million is just a number, pick something big. There's no good rule of thumb, but I'm cheating here. I know the answer, so I pick a number that's big enough to show them, but we do that. And it's pretty amazing. There's 20%, sorry, 2% only that you are sick, which is very, very surprising. Most people say, what? But the test is accurate 95% of the time. But still, because the chances that you are actually sick is 1 in 1,000, the actual percent that you're truly sick is just 2%. And most people get it wrong, which is sadly not so good. The last one is a known problem. This is known as the Monte Hall problem. And it describes a game. And the game says there are 3 doors, and they are closed at the beginning. And you need to pick, and they tell you, behind one door there is a car, and behind the 2 other doors there are goats. And we assume that you want to win the car, not the goats. So pick a door. So you pick a door. Once you pick a door, the host is coming in and opens the door and shows, here, you see behind this door there is a goat. Now, would you like to stick with your original decision, with your original door? Let's say I picked 1. Do you want to stick with 1? Or do you want to change door to door number 2? Okay, so what is the strategy? Do I stick with the door I chose, or do I switch once I know? And if you Google this problem, there are debates like crazy on this issue. So let's look at the Monte. Okay, so I'm going to write a function saying that did the stay strategy won a game? Okay, so I'm simulating a game. So this is the door that the car has, that has the car behind it, and this is the door that the player chose. And now, if the player chose to stay, then they won. And if the player, if the car was in the same door that the player chose, then the strategy of staying on the same door you initially choose wins. Otherwise, the other one wins. And this is just to calculate a fraction. And then we're going to run simulation. And the simulation is going to give us the fraction of games that the win strategy won, and the fraction of games that the switch strategy won. Okay, so we start by initializing the game, and then we say if stay wins the game, we increment the number of the wins for the stay strategy. Otherwise, we increment the number of the wins for the switch strategy. And finally, we return the fractions. And again, we're going to do 1,000,000, and I'm going to say it as a percentage this time.
Okay, could you scroll up for a second again to the initial function? Yes. I'm just trying to comprehend what you said before. So in the first case, someone's gonna pick a number, and then the host comes in and opens another door, which he didn't.
Yeah, but he opens always a door that has a goat around behind it. So the door they open always has a goat. So now you have only 2 doors to pick from.
Yeah, but are they only just? Yeah, you pick from 2 doors, but you say rand int 3, so you basically have 0 to 2. So you have 3 choices again.
This is the initial guess. So there is car behind one of the doors, and then the player pick another door. And now the host is opening one door, but this is happening after this, after line 13. So here host reveals the door with the goat. Yeah, and I cannot spell it. Okay, so now the host reveals, and now in your strategy, if you're staying, it means that you're going to win only if it was you initially guessed correctly. Otherwise, if you switch, then this is the car with the door, because that's the other option.
Yes. Okay.
Okay. Okay. So by a factor of 2, it is much better to switch those, which is really, really counterintuitive. Like, how is the fact that someone showed me something after I chose is going to affect my odds of winning? And I won't go into why. There is a lot of explanation, a lot of debates. I read it several times. I think I have it right, but in these cases, just go write a program and.
But in your logic, you're not switching, right? You're just calculating 2 random ints between 0 and 2.
And then I'm saying
obviously you have a chance of 1 to 3 to get the same numbers.
Yeah. So this is a single game. So in a single game, I'm saying which strategy won, and here on the simulation, I'm counting how many times this strategy won and how many times this strategy won. And then I return the fractions.
Okay, maybe I'm just misunderstanding the problem then.
So what we want to do is simulate like a lot of games, and in every game we want to see which strategy is going to win. Is the strategy of staying with your initial guess, or is going to give you the car, or is the strategy of switching a door going to give you a car? So what we have in line 11 to 16 is just a simulation of a single game. So this is a simulation of a single game saying which strategy won. Basically, it's saying if the stay strategy won, and then if it didn't, then the other strategy is going to win. And then in lines 25 onward, we're going to run 1,000,000 games and say what were, in every game, which strategy won. And finally, return the fraction for both of them. And doing the math, it's harder. Me as a developer, for me to running these things is easy. So if you want to learn more, there is a great talk by Jake Vanderplas that I mentioned called Statistics for Hackers. It's in Python, but again, the coder is a for loop and random number. That's roughly what he does there. And he does much more magic than I'm doing here. And you can read in general about the Monte Carlo simulation. But the main idea is that simulations are a super effective tool. You don't need a lot of math to understand them. Most of the problems here, right, it's just running a for loop and a random number generator, and you're good to go. So, when you talk with people in statistics, and sometimes even with people who are doing data science and algorithm, they say, yeah, it's a tool, we use it. It's very easy to use, it's really easy to reason. And after that, if you want to go deeper and understand the results, then we do the math. But the initial one is pretty easy. And that's it. Thank you very much. for hosting me. Any more questions? Okay, so this link, and I'm going to post it later on in a comment in the meetup, is where you can see both these slides and all the code that I wrote. It's available. Thank you very much.
Thank you.